we're going to do some applications of exponential functions. So we're going to talk about things that are growing or decreasing at a constant rate, which there's this fancy looking formula for it that they like to use where y sub 0 is the starting amount, t is the amount of time, and k stands for the rate of growth. Really, it's the same as the continuously compounded interest formula, so I'm going to use those letters instead because I don't like the sub-zero and the k, and yeah, I'd rather just write it with the form you've already been using. So say that this is my exponential growth function for population. I want to predict the world population in 2018. T stands for the number of years after 1999. So 2018 minus 1999, it's 9 years after 1999. So my value for t that I'm going to plug in is 9. So I'll have 6 times 0.0121 times 9. Make sure you put those parentheses in your exponent. If you punch it into a calculator, you're going to get approximately 7.55 billion people in the year 2018. A quick little just explanation. Remember, 6 stands for the starting amount, so your population in 1999 would be 6 billion. The 0.0121 tells you the population's increasing at 1.21%. We're going to turn this around. We want to know in what year the population will reach 8 billion. So we're looking for an ending population of 8 billion. And we're going to be solving for the amount of time that it takes that to happen. So I'm going to get my exponential part, divide both sides by 6. Gives you 4/3 equals your exponential part. And then to undo an exponential function, solve for t, I am going to have to do natural log base e of both sides, which will just give me natural log of 4/3 equals 0.0121. T, I realize I left that off in my exponent before. Should be that. Divide to get t by itself. And then if you punch that into a calculator, you should get approximately, for your number of years, t is 23.78 years to reach 8 billion. Now it asks what year that's going to happen in, so that's how many years it is after 1999. So if I add 24 years approximately to that, that puts me in the year 2023. Let's do a little college tuition modeling. Always fun times. So say that we've got college tuition in 2017-18 is $7,000. It's increasing at a rate of 8% per year. We want to figure out what the tuition will be after 3 years. So I kind of set this up, highlighting my rate's 8%. My starting tuition I'm looking at $7,000, and I'm looking for the tuition in 3 years. Had to search for it because it was written out. If I plug those values in, that should give me my expected tuition cost 3 years after I started. So in 2020, 2021. Plug that value in, and that gives you approximately $8,898.74, which 3 years later, $2,000 more. That's rough. It says 22 up above here. Ignore that. I screwed up and had to fix it. Now we're looking for how many years it will take for our tuition to quadruple. So quadrupling my start amount of $7,000 means I'm looking when my tuition will end up as $28,000. Same rate of growth. This time I'm solving for t. So kind of like before, these all kind of go the same way. Get your exponential function by itself, and then take the natural log of both sides of your equation, which will give you natural log of 4 is equal to 0.08t. Running out of space, let me erase. Divide by 0.08, and that should give you how long it's going to take for tuition to quadruple. So approximately, it's just the school, 17 years. Okay, a little chemistry for you. So we've got this substance and it's decreasing in an amount, but we don't know the rate at which it's decreasing. So this is kind of going to be a two-step process. So first off, we need to find the rate at which the amount of our substance is decreasing. We do know the starting and ending amounts, and that it takes 2 years to go from 300 grams down to 100 grams. So I can use those pieces of information to figure out my rate of decrease in my radioactive substance. So if I plug in what I know, I'm gonna have it set up like that. I could divide to get 1/3 equals e to the 2r power. Again, natural log's your favorite on these. Base e functions, natural log of both sides. You'll have natural log of 1/3, and then you will have to divide that by 2, because that's what 2r equals, which is going to give you that your radioactive substances amount is decreasing by negative 54% each year. Now you have enough information to actually write your full exponential function for our situation. So we know we start with 300 grams, e to the negative 0.5493 power, and we're looking for the amount after 5 years. So if I plug all that in, you should end up with approximately 19.245 grams after 5 years. Things we're interested in chemistry are sometimes the half-life of a substance, which is just the time that it takes for half of the original amount to be remaining. So I can solve this by figuring out what is half of my original amount. So if I started with 300 grams, half of 300 grams would give me that I'm looking for the amount of time it takes to get to 150 grams. So let's put in our equation 150 grams for our ending amount. When we start with 300 grams, still the same substance, so still the same rate of change there in our exponent. Divide gets you 1/2, and then do your natural log of both sides of your equation. Might have noticed, well, I divided, so it got me 1/2 for my half-life. Is that always going to be true? Yeah, it is. If you want like the time it takes to get 1/3 of the amount, you could just set it equal to 1/3. But anyways, if you solve your equation, you're going to end up with, takes a lot of time to write things down here, approximately, for my half-life, 1.26 years to get down to half of my original. All right, I'm going to have you guys try this one.